Hi everyone. I'm going to do a quick introduction on the typical types of bridges that we see at Troitsky competitions. The first thing to consider when you're looking at these types of bridges is that they're going to be subjected to only a single point load in the middle. No lateral loads, earthquake loads, wind loads, for example, or uniform distributed loads like you would see on actual bridges. Additionally, you're not going to have any moment or lateral reactions at your foundations, just vertical, which eliminates certain types of bridges like suspension bridges and cable stayed bridges. When you're doing certain types of bridges, you have to put a tensile member on the bottom to prevent it from buckling. I'll show you some examples of that later on. To start off, we have beam bridges, which transfer load to the foundation through shear. They're really easy to build. They're also easy to analyze, and you get a low height bonus, which I'll show you in a second. The problem with them is that they're just not as efficient as other designs in theory. Here are the bonuses that you're going to see. So low bridges get better bonuses. This bridge that you can see here is less than 300 millimeters tall, so it got the full 10-point bonus. And then also there's weight penalties. It's pretty easy to control the weight of a beam, so you're not going to get dinged for that. This bridge that you can see here actually won the competition, and it's really just a brick with two supports at either side. So you can do that, and there's nothing shameful about it. Next up, we have truss bridges, which I'm sure you're all very familiar with. They transfer load to the foundation through axial members as well as strong joints. They are easy to analyze. They work well with the size limit to competition. So you can't bring an assembled bridge to the competition. It has to come in certain size pieces. And by definition, an unassembled truss bridge is just a bunch of pieces. So it just kind of works well. And it also will have decent structural efficiency. The problem with truss bridges is that it can be really, really difficult to do joints, and it can be a lot of work to assemble in the 3 hours that you have. A lot of teams run into problems with that, where they're running up against the deadline. Here's some truss bridges. You can see the one on the left. The joints are not phenomenal, kind of cobbled together, and this bridge, I can tell you, it was my bridge, not very impressive. And then the one on the left had just been crushed, so that's just fun to see. You can also do, and I would encourage you to look into this, you can do hybrids. So this is kind of a hybrid beam truss bridge. Lots of fun to look into, lots of fun to do. They can do really well at competition too, hybrid bridges. Next up, we have arch bridges. So they transfer load to the arch through axial members, which are in this case connected to the middle. This is important because you only have a point load, so there's no point putting tensile members that are going to transfer the load from different parts of the deck. You just want it connected to the middle kind of thing. And then from the arch it will go into the foundations. And the other important thing to consider here is to prevent the entire thing from just buckling out when you put any load on it. You need to have a tensile member along the bottom. Arch bridges are theoretically the most structurally efficient legal bridge that you can build, but they're very difficult to build well, and they're also difficult to design and analyze. Here are some examples of arch bridges. These are just really impressive bridges as a whole, if you can pull it off. The one on the bottom is also kind of a hybrid of a type of bridge I'm going to show you in a moment, an arch bridge. And then this bridge here was the only bridge I've ever seen that was not crushed by the hydraulic press, which is insane. These guys won the competition, and they had their bridge on the banquet table when the trophy was presented to them. It looked like it looked before it went under the press. It was insane. And last up, we have A-frame bridges. This bridge here is kind of a cross between an arch and an A-frame, but these are essentially just triangular bridges tailored for having a point load in the middle, and they also require a tensile member along the bottom. They are even more efficient than arch bridges in this situation, and they're also easier to build than arch bridges, which is kind of a big deal. And the problem with it is that it's illegal. So there's kind of ways around this. People pretty much always manage to bring bridges that are essentially A-frames, but you have to be very careful with the rules that are set out to not be eliminated. And they're also not very applicable to actual design in the real world. Elements of them are, but you're not ever going to build a bridge that is only tailored for a point load in the middle and no other loads. These things would collapse if they were, ever put into use in the real world. Here are some examples of A-frame bridges. Lots of fun. They're kind of cool looking, I guess, and they perform pretty well. That's all the bridges I'm going to show you for today. My last piece of advice is that if you want to do well at the competition, design a bridge to meet all the specifications and also have it easy to assemble at competition. That's a really big deal. So, jigsaw pieces in some cases. Alright, so that's it for this short video. I would encourage you to look at the rulebook. I believe Cam made a video overviewing what's in the rulebook. I would encourage you to watch that. And everybody have a great day.